Hello, welcome to a new lesson in differential equations. Today we are going to make an example of how to find the green function associated to a differential equation. Recall that this is a method that has to do with a second order linear non-homogeneous differential equations, and we have made recent lessons talking about the theory behind the green function. So it is important for you to check those previous lessons to understand the steps that we are going to follow in this lesson. Okay, so the problem that we are going to solve today is the one that I have written here. It is that the second derivative with respect to x of y minus k squared y of x is equal to some arbitrary function f of x. And you know that this differential equation has to be defined on a certain interval, and we need to have some boundary conditions to work with. Okay, so we know that we have that if we have a differential equation of this form, we can associate a green function, which is a function of two variables, in this case, that has to satisfy the next relation. We will have that the second derivative with respect to x of the green function, which is a function of x and x prime, then minus k squared, the green function, is equal to the Dirac delta like this. Okay, and we know that for a given x prime that is between 0 and L, we can split the problem into two pieces. We can define a green function that is going to be of one form between 0 and x prime, and then from x prime to L, it will have a different form. So we are going to define it in the following way. We will have that the green function of x comma x prime is equal to, and it will be g1 of x comma x prime equal to, let's say, a function of x prime that multiplies e to the kx plus b of x prime e to the negative kx. And like I mentioned, this is for the interval where x is between 0 and x prime. So it will be 0 less than or equal to x less than or equal to x prime, which is of course less than or equal to L. Here our variable of interest is the x, okay? So, I'm proposing this structure of the green function because we know that, the solution to the homogeneous version of this equation that I have here, is of the form of a linear combination of exponential functions, right? So that's the motivation to propose the green function as this. You know that in that case, we usually have some constants here, but looking that we are working with a two-variable function, we are going to consider that constant as a function of the x prime, right? So it can be a number, maybe just a constant, but in this case, just to generalize, we are using a function of the variable x prime. Okay, and the second piece of the green function, is going to be of the same form, but with a different constants or different functions in this step. So it will be c of x prime e to the kx plus d of x prime e to the negative kx if x is now between x prime and L. So it will be 0 less than or equal to x prime less than or equal to x less than or equal to L. Okay, so this is the green function that we are going to work with, or we are going to propose. So the goal here is to find a, b, c, and d to construct the green function. And to do that, we are going to make use of the boundary conditions and some other things that we found on previous lessons these things have to do with continuity and the continuity of the derivative of the green function, right? And that's why it is important for you to check the previous lesson about the green function that I led you in the description of the video. So if we use the first boundary condition that tells us that at x equals 0, the green function is equal to 0, and this is because, well, we have this boundary condition for y. We know that if y satisfies this condition, well, looking that the green function satisfies this differential equation that has the same structure of the initial differential equation, well, it has to satisfy the same boundary condition as y, right? So we have this where x is equal to 0, right? So if we make use of this condition, we are going to get here that a of x prime e to the 0 plus b of x prime e to the 0 is equal to 0. And this gives us that b of x prime is equal to negative a of x prime. Okay, then we are going to make use of the second boundary condition, which tells us that g evaluated at L comma x prime is equal to 0. And then, well, this implies, let me write an equal sign, that c of x prime e to the kl plus d of x prime e to the negative kl, right? So what do we get from here? We are going to multiply both sides of this equation by e to the kl to get that 0 is equal to c of x prime e to the 2kl plus d of x prime. This akl will cancel this a to the negative kl. And from here we get that d of x prime is equal to negative c of x prime e to the 2kl. Perfect. So with this, we have found two equations that will help us to find the functions that we need to construct the green function. So we are going to take these results into the definition of the green function that we proposed. So we will have that g of x comma x prime is equal to, it will be a of x prime e to the kx plus b, which is minus a of x prime, e to the negative kx, right? I'm not going to write the interval of definition just for simplicity. So from here we get that this is a of x prime that multiplies e to the kx minus e to the negative kx. And then on the other side we will have c of x prime e to the kx plus a d, right? But d is this thing over here. So it will be minus c of x prime e to the 2kl times e to the negative kx. And this is equal, factoring c of x prime. We will have that this multiplies e to the kx minus e to the 2kl e to the negative kx. And as you should know, well, this has a very similar structure to the hyperbolic trigonometric functions, right? Let's recall that the hyperbolic sine of x is equal to e to the x minus e to the negative x divided by 2. And the hyperbolic cosine of x is equal to e to the x plus e to the negative x divided by 2. Okay, so we see that this thing that we have here is actually this thing, but just with, instead of x, we have kx, right? So we can see this as 2 times the hyperbolic sine of kx. Okay, so let me write that. So we will have that the green function is a of x prime times 2 times the hyperbolic sine of kx, of course. Okay, this is for the first part. Okay, so now let's work a little bit with this expression that we have here. So what are we going to get in that step? Well, we have e to the kx minus e to the 2kl e to the negative kx. So what we are going to do here is to multiply on the numerator and in the denominator by e to the negative kl, like this, right? So we are going to get the next. It will be e to the kx minus kl minus e to the kl minus kx, and then all divided by e to the negative kl. Okay, so from here, well, it is not hard to see that this is e to the k times x minus l minus e to the minus k x minus l divided by e to the negative kl. So again, we see that this piece over here is 2 times the hyperbolic sign of the exponent, right? So this thing can be seen as 2 times the hyperbolic sign of k times x minus l, like this. So all this thing is 2 e to the kl, just by taking this to the numerator, and then the hyperbolic sign of k times x minus l. Okay, so this means that the second piece of the green function is going to be of the form c of x prime 2 times e to the kl, the hyperbolic sign of k times x minus l. Okay, and just for simplicity, we are going to transform this part of the definition and this other part of the definition to some new functions of x prime, just to eliminate the constant 2, to get that g of x comma x prime is going to be defined as follows. Here we will get alpha of x prime sine the hyperbolic sign of kx, and then beta of x prime e to the kl, the hyperbolic sign of k times x minus l. Okay, yep, so this is just another way to reduce the definition of the green function, but we still need to find the shape of alpha and beta, right? Okay, so here is where we are going to use one of the concepts that we introduced on the previous lessons that we made about the green function, where we mentioned that exactly at the point x prime, well, we know that the green function has to be continuous. Okay, so that means that evaluated at x prime, these two pieces have to be equal. Recall that this is g1 and this is g2, right? So g1 and g2 have to be equal evaluated at x prime. So this can be written mathematically in the following way. g1 of x prime comma x prime has to be equal to g2 of x prime and x prime. So this is very easy to express. We are going to have that alpha of x prime, the hyperbolic sign of kx prime, should be equal to, well, this thing evaluated at x prime, but we are going to write it as minus b of x prime e to the kl, the hyperbolic sign of k times x prime minus l equal to 0. Okay, so this is equivalent. Perfect. So with this, we have a first equation that is going to help us to find alpha and beta. Right now, we need to find a second equation of alpha and beta, and with two equations of two variables, well, we know that we can solve the system of equations to find alpha and beta. So again, using one of the concepts that we have been working with, that the derivative of the green function at x prime, it is not continuous, right? So we have an equation that relates the left derivative and the right derivative, that will help us to find, this new equation that we need. But just to remember, we're going to make this process on a different way, just to for you to remember where this property come from. Okay, so we are going to start by writing again the differential equation that defines the green function. So we know that that equation is double prime of g of x comma x prime minus k squared g of x comma x prime is equal to the Dirac delta, like this. Okay, so what we are going to do is to integrate both sides of this equation on a neighborhood of x prime. Okay, and we are going to make that a neighborhood to be smaller and smaller to see what we get. So we can see this as the integral from x prime minus epsilon to x prime plus epsilon, and this is an integral of dx, of course. And here we have the integral from x prime minus epsilon to x prime plus epsilon. Okay, so let's split this into two integrals to have that this is the integral from x prime minus epsilon to x prime plus epsilon of the second derivative of g dx, and then minus k squared, the integral from x prime minus epsilon to x prime plus epsilon of g dx, and we know that this is equal to, well, this integral that we have here. But looking at, of course, this x prime is inside the interval of integration. Well, we know that the integral of the Dirac delta in this case, well, it should be equal to 1, right? Okay, perfect. And looking at, we know that the green function, well, is a well-behaved function, a continuous function on x prime. We can see that when epsilon goes to 0, well, this is just going to be an integral that goes from x prime to x prime of, again, a continuous function, right, at x prime. So that means that this integral is going to be equal to 0, right? Looking at, well, again, the green function is continuous at x prime. So as epsilon goes to 0, well, this is the integral from the same limit, the same down and upper limit. So we know that the integral in this case is equal to 0, right? All the time. Okay, so, and in this step, we have the derivative of g, right? So if we have the integral of the derivative of something, in this case, looking that it is with respect to x, we know that we can cancel the derivative with the integral, taking the limit where epsilon goes to 0, right? Remember that we do not know if the derivative is continuous at x prime. Okay, so we cannot say that this is equal to 0 in this case. Okay, so this means that taking the integral where epsilon goes to 0, here we are going to get the derivative with respect to x of g of x comma x prime evaluated from x prime minus epsilon to x prime plus epsilon. Again, just by canceling the integral with the derivative. Okay, and this is equal to 1. Perfect. So from here, what are we going to get? Well, we know that evaluating this limit at this derivative, well, it's going to give us the function evaluated at x prime, but from the right. So it will be the derivative with respect to x of g evaluated at x prime from the right x prime. And then by the fundamental theorem of calculus, we have a minus here, the derivative with respect to x of g of x prime minus here, and then x prime. Yeah, like this. Recall that here we are evaluating g from the left. Okay, so this is equal to 1. Okay, so if we want to calculate the derivative of g from the right, well, we know that we need to take this definition of g, of course, because this is at the right of x prime. Let me write it. This is when x is greater than x prime, right? Greater or equal. So this means that if we want to calculate the derivative, well, we need to take the structure that we have here. Okay, so what is going to be that derivative? Well, first of all, looking that it is with respect to x, this beta of x prime is like a constant, and then this multiplies e to the kl, and then the hyperbolic sign of k times x minus l. So the derivative of the hyperbolic sign is just the hyperbolic cosine, and then this multiplies k times x minus l, And then we need to take the derivative with respect to x of the argument of the cosine, but that is just a k, okay? And then minus, and now we are taking the derivative of the green function from the left of x prime. So we know that in our definition, the green function that we need to consider is this one over here, because here x is less than or equal to x prime. Okay, so that means that we need to take the derivative of the hyperbolic sign of kx. So we will get alpha of x prime k cosine, well, the hyperbolic cosine of kx, and this is equal to 1. Remember that in hyperbolic trigonometric functions, the derivative of the cosine is equal to the sine, not the minus sign. Like in trigonometric regular functions, we know that when we take the derivative of the cosine, we get negative the sine. Well, in the hyperbolic functions, that doesn't happen. Okay, and recall that, well, this is evaluated at x prime, right? So this x is actually an x prime. Okay, so with this, we can construct the second equation of our system of equations. So we will have minus alpha of x prime cosine of kx prime, and then plus beta of x prime cosine, well, e to the kl cosine of k times x prime minus l. And let's write this as 1 over k, just by taking these two k's to divide on the right-hand side of the equation. Okay, so this is the second equation that we are going to use to find alpha and beta. And by now, we are going to use the Cramer rule. Let me make some space to write the equations together. Okay, so this is the system of equations that we need to solve. So we are going to make use of the Cramer rule to see that alpha of x prime is equal to, well, it will be the determinant of 0, 1 over k here, and then minus e to the kl, the hyperbolic sign of k times x prime minus l. And here it will be e to the kl, the cosine of k times x prime minus l. Okay, and then this is divided by, well, the determinant of the hyperbolic sign of kx prime minus the hyperbolic cosine of kx prime minus e to the kl, the hyperbolic sign of k times x prime minus l, and then e to the kl cosine of k times x prime minus l. Okay, so from here we are going to get that this is e to the kl divided by k, the hyperbolic sign of k times x prime minus l, divided by, it will be e to the kl, the hyperbolic sign of k x prime, the hyperbolic cosine of k times x prime minus l, and then minus e to the kl, the hyperbolic cosine of kx prime, and then the hyperbolic sign of k times x prime minus l. Okay, so I think that we need to work a little bit with this expression, right? To simplify just by using trigonometric identities. But we see here that we can cancel this AKL with this and this. Okay, so this will be the hyperbolic sign of k times x prime minus l divided by k. And then here we are going to have the hyperbolic sign of kx prime times, it will be the hyperbolic cosine of kx prime, the hyperbolic cosine of kl, minus the hyperbolic sine of kx prime, and then the hyperbolic sine of kl. Okay, And then here we are going to have minus the hyperbolic cosine of kx prime that will multiply the hyperbolic sine of kx prime, the hyperbolic cosine of kl, and then minus, it will be the hyperbolic sine of kl times the hyperbolic cosine of kx prime, like this. And we close this bracket here. Perfect. Okay, so I think that some terms should cancel. So we see that actually this term will cancel with this term, right? Okay, so we are going to get the hyperbolic sine of k times x prime minus l divided by k that multiplies. Notice that we have a common factor, the hyperbolic sine of kl here and here. So let me take out that common factor. To get that, well, we have sine of kl that multiplies minus sine squared of kx prime. And here we have plus cosine squared of kx prime. Okay. Well, you should know that in hyperbolic functions, the Pythagorean identity for the sine and the cosine is the next. The cosine squared, or the hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to 1. So that is exactly that we have here, right? Recall, in this case, we have a minus sign. So it is important for you to remember that aspect to say that this is equal to 1. Okay, and then this is equal to the hyperbolic sine of k times x prime minus l divided by k times the hyperbolic sine of kl. And this is equal to alpha of x prime. Perfect. So with this, we have found the first part of the system of equations, well, the alpha part. So we need to find now what is beta of x prime. So this is going to be, well, at the denominator, we will have the same as we had before, right? Recall that in the first part of alpha, we canceled a common factor e to the kl because here we have an e to the kl on the numerator. But you will see that that will not happen for beta. So we will have here e to the kl and then sine of kl. Perfect. And for beta, we will have that here is going to be the hyperbolic sine of kx prime, and then minus the hyperbolic cosine of kx prime, and then 0 and 1 divided by k. Okay, so this is going to be the hyperbolic sine of kx prime divided by k times e to the kl, the hyperbolic sine of kl. Okay, so with this, we can now construct what is the complete form of the green function. So let me just remark what is beta of x prime. And then we said that the green function can be defined in this manner. Where is it? It is here, right? So we have this. Now we have the values of alpha and beta. So we just need to substitute what we found. Okay, so here we are going to have the hyperbolic sine of kx times alpha, which is the hyperbolic sine of k times x prime minus l divided by k times the hyperbolic sine of kl. And this is from 0, which is less than or equal to x, less than or equal to x prime, less than or equal to l. And for the second piece, we had that e to the kl multiplies the hyperbolic sine of k times x minus l, and this multiplies beta of x prime, which is the hyperbolic sine of kx prime, divided by k e to the kl, the hyperbolic sign of kl. So if we cancel these things and we write that this is from 0 less than or equal to x prime less than or equal to x less than or equal to L. With this, we have completed the definition of the green function associated to the differential equation that I showed at the beginning of the video. Okay, from here, we know that then the solution of the differential equation can be seen as the integral over the region where the green function is defined as a subset of R2 of the green function times f of x dx, where f of x, I remember that, well, it is the non-homogeneous term of the differential equation. Okay, recall that this is a theorem that we showed on the previous lesson talking about the green function. We showed that for a particular differential equation of that form, we find a green function that satisfies the differential equation that we showed at the beginning of the lesson, and then we showed that if we construct a solution of this form, well, it satisfies the differential equation. In this case, well, we may need to split this integral into two pieces, right? Because we have the definition of the green function for two parts. So one will be in this interval and the other one in this interval. But the thing here is that the solution of the differential equation can be seen as an integral of this form, where g is, of course, this huge thing that we found. Perfect. So I think that with this is enough. I think I will finish the lesson here. Thank you so much for watching.